Continuing our series on experiments, we're going to look at fractional factorial experiments that are built off original 2 to the k's. As we look at fractional factorial experiments in this section, we'll look at the different kinds of designs, the downside of fractional factorials, the confounding effects, and then the nomenclature or experimental resolution of the different types of fractionals we can run. Why do we use fractional factorial experiments? As the name implies, we take a base 2 to the k experiment and we run a fraction of it. We do that to limit or reduce the number of runs. So if we still have quite a few x's in our experiment, we can limit the number of runs by running these fractional designs. As we showed in the last section, that every time we add an x to the mix, we're going to double the size of the previous experiment. So you can see we can get quickly into the hundreds of runs, and not only would the length of the experiment be difficult, but also the setup of the columns for all of the treatment combinations we would have to consider. So thinking about having a number of equations and a number of unknowns, we can see as we get higher in the number of x's that there might be some coefficients that we might not be interested in. So in a 2 to the 5 experiment, we have 32 equations, 32 treatment combinations, and we could estimate up to 31 unknowns just using algebra. Well, okay, so yes, we always want to look for an intercept. We want to look for how the main effect of each x, so we'd be interested in all of these slopes for x1 through x5. And yes, we would be interested in the two-factor interactions, and with 5 x's, there are 10 of them. So we have 10 plus 5, so about 16 of the coefficients are pretty important. That's only half of the number of runs, and thus the idea of this fractional experiment comes into play. So we're going to take a look at these really high order interactions and use them to our advantage in looking at, can we reduce the number of experimental runs, because maybe we don't need to estimate these particular beta coefficients. So here we've got, there's 10 three-way interactions, 5 four-way interactions, and even a mammoth 5-way interaction where you'd have a term that's x1 times x2 times x3 times x4 times x5. And so we're going to ask ourselves, should we solve for these 31 coefficients? Can we reduce the size of the experiment, or could we add other x's so for the same 32 runs I could get even more information? Building off what we looked at on the last slide for a 5-factor experiment, 5 x's, that we might be using half our data to estimate these 3-way, 4-way, and 5-way interactions. So runs 17 through 32 are used to estimate these higher order terms. And what we've found over time, many years of running these types of experiments, that we really have a quick fall off on whether those terms would ever be statistically significant. And then my further contention is, then what would I do with that term, even if I knew that it belonged in my regression equation? How would I interpret those results? So we already saw the 2-way interactions and how we look at those to see that maybe the slope of one x changes as we change the factor level of the other. So we get these v's, or these total crosses, in our interaction plot. Well, now we have to add a third dimension to get that 3-way interaction. And would that be useful in setting X values that would optimize Y. And so we're typically after these main effects and two-way interactions, so can we use that to our advantage to shrink the size of the experiment or keep the experiment size the same but add additional X's to the number of columns. In the last two slides we were showing you the sparsity of effects principle, that we're typically interested in main effects and two-factor interactions. And if that's the case, then we shouldn't spend a lot of time chasing after the three-factor and higher with the same cost per term by adding them to the experiment. So if we assume them to be negligible, we can then reuse those runs for other factors, or we can shrink the size of the experiment. A couple other properties that are nice with fractional factorials is they have a projection property. So consider that if I ran a half fraction of an experiment, so only half the runs, well, we saw that experiments double as we add another X. Well, if an X falls out, the p-value is greater than 0.05, well, likely what I'm left with is a full factorial in the X's that are important. And I was able to throw out an X while running a smaller experiment. So it has this projection property. And then I can also add fractions together. So if I run a half fraction and a half fraction, I add them together, I can have a full factorial experiment. And we can do that with 4/4, we can do that with 8/8. So we can continue to build on the knowledge of an experiment and eventually get to a full factorial if we need to. Now, what I find most of the time is we learn so much by running an experiment that we would never design it exactly the same way the second time. But mathematically, we can add fractions together and come up with a full 2 to the k if that was the best route to go. Nomenclature for fractional factorials. It gets really kind of funny in here. So there's our 2 to the k. So that's our base design. So that should look familiar. We're going to start out with, this is the experiment it would be if we ran a full factorial. Then we're going to subtract the fraction. So what is the degree of our fraction? So when p equals to 1, it's a half fraction. When p equals to 2, it's a quarter fraction, and so on. And then we have this thing down here called R, which is the design resolution. And we're going to get into that into some detail. There are many different types of resolutions. We're going to specifically look at 3, 4, and 5 or greater, which are essentially full factorials.